morning. I'm Fasiha and I will now start this presentation of the topic 7, which is a free radical reaction. So first foremost, let me explain the most important part of this presentation, which is the definition of the free radical. So what is a free radical? Free radical is a species in which it could be atom, molecule, or even ion that has unpair of electron. And this free radical species is formed through the non-polar bond breaking. It is well known with its properties, which is unstable and very reactive. So now let's moving on to the next part, which is the fission. Fission is divided into two, hemolytic fission and heterolytic fission. So basically, fission is a bond breaking or bond cleavage. Hemolytic fission is a fission in which the bond will break evenly and pair of electrons will be shared equally and produce a free radical species. Usually this kind of the bond cleavage will be applied in the non-polar molecule bond breaking. And it is required energy such as UV light and heat in order to proceed with this reaction to weaken the bond easily. So for example, here we have is a chlorine gases. So chlorine gases is a non-polar molecule. So of course it will apply the hemolytic fission to break the bond between the chlorine gases and produce the free radical species of chlorine. Heterolytic fission. Heterolytic fission is opposite to the hemolytic, in which the bond will break unevenly and pair of electrons will be shared unequally and produce whether cation or anion. And usually this kind of bond cleavage will be applied on a polar molecules such as hydrochloric acid and others. So for example, here we have is a nucleophilic substitution reaction of the bromomethane. We know that methane is a less electronegativity species, while bromine is a more electronegativity species. So methane will lessly attract pair of electron and produce carbocation, while the bromine, which is more electronegativity, it will attract pair of electron and produce an ion of a bromine ion.
The mechanism of free radical reaction consists of three main stages, which are initiation, propagation, and termination. The reaction begins with the initiation stage, where initial free radicals are generated through homolytic cleavage. A halogen molecule such as chlorine is exposed to UV light or heat. The energy supplied causes the chlorine-chlorine bond to break evenly, with each chlorine atom taking one electron from the bond, thus forming two chlorine free radicals. As a result, the number of radicals increases from 0 to 2. The reaction then proceeds to the propagation stage, which is responsible for maintaining the chain reaction. A chlorine radical abstracts a hydrogen atom from an alkene molecule, producing hydrochloric acid and an alkyl radical. The alkyl radical subsequently reacts with a chlorine molecule, forming the desired product, which is an alkyl halide, while generating a new chlorine radical. Throughout this process, the number of free radicals remain constant, allowing the reaction to continue. Eventually, the reaction reaches the termination stage, which is the last stage. At this point, two free radicals combine to form a stable product, causing the chain reaction to stop. For example, the coupling of two chlorine radicals produces a stable chlorine molecule, and the number of free radicals decreases to 0, marking the end of the reaction.
Now, I'm going to explain the stability of radicals. The stability of radicals can be explained by alkyl substitution. As the number of alkyl groups on a carbon-bearing free radical increases, the stability also increases. The increasement can go from the methyl radical to primary, secondary, and lastly, is tertiary. So the electron poor species are stabilized by neighboring atoms that don't need electrons. Next, we have resonance stabilization. Allylic and benzylic are the most stable radicals. This is because the radicals are next to a double bond. The double bond and radical are able to switch places through resonance structure. This will cause delocalized electron deficiency over several atoms. Last but not least, we have bond dissociation energies. As we go down the periodic table, it will increase the radical stability. This is because the partially filled orbital at a more larger atom, and also it is further away from the positively charged nucleus. So, the electron deficiency also spreads at a greater volume. Let's continue with the radical addition to a double bond. So, in initiation, the formation of radicals from peroxide occurs. This is because heat causes homolytic cleavage of the weak OO bond in the peroxide, and the oxygen takes one electron, forming two alkoxy radicals. Then, the formation of bromine radical occurs. The alkoxy radical is very reactive. It abstracts a hydrogen atom from HBr, in which cause a product which is alcohol and also a bromine radical. The bromine radical is used in propagation. In propagation steps repeat continuously and keep the reaction going. So firstly, the addition of bromine radical to alkene. The bromine radical adds to the double bond. One pi bond bonds with Br, and the other becomes carbon radical. The radical forms at the more substituted carbon, giving a tertiary free radical because it is more stable. Next, the reaction of carbon radical with HBr. The carbon radical removes a hydrogen from HBr, forming a bromoalkane and also another new bromine radical. The newly formed bromine radical continues the chain by attacking another alkene. Lastly, we have termination. Termination occurs when radicals combine and no new other radicals are formed. This can happen by radical-radical combination, in which two bromine radicals combine to form bromine, or carbon radical plus bromine radical to form a bromoalkane, or lastly, a carbon radical plus a carbon radical in which two organic radicals join, forming a larger molecule. These steps stop the reaction because the radicals are destroyed.
Next, we move on to the example of free radical reaction, which is free radical substitution, where the process occurs when alkene react with halogen producing haloalkane. When we talk about substitution, it suggests that we need two species involved so that each of them can exchange part of each other. One of the species involved need to produce a free radical which typically group 17 halogen molecule, such as chlorine, and other species need to be an alkene. From this equation, we can see that the hydrogen atom has been substituted with chlorine atom from chlorine molecule, likewise creating a byproduct as a result. Free radical reaction actually involve in a chain reaction consisting of three main steps, which is initiation, propagation, and termination. For the initiation process, the ultraviolet light provides the energy to break the bond between the chlorine molecule in a process homolytic fusion. Since covalent bond consists of two electrons, homolytic fusion will cause the each shared electron in the bond to be split mutually between the two chlorine atoms, forming two chlorine radicals, and use half arrows to represent the movement of these single unpaired electrons. Next, for the propagation step, since the chlorine radicals are extremely reactive, they collide with the methane molecule around them and abstract one of their hydrogen atoms. Since the CH covalent bond consists of two shared electrons, electron from the hydrogen will join the unpaired electron of chlorine radical to form a stable covalent HCl bond. Then, the remaining unpaired electron from the CH bond will return to the central carbon atom, forming another highly reactive radical. Next, the methyl radical will react with the stable chlorine molecule abstracting a chlorine atom in the same way like before, which forming chloromethane and regenerating chlorine radicals. This chlorine molecule will react with another methane molecule and whole propagation process repeated infinitely. That's why we need the last step, which is termination step, which can break the infinite loop. In this step, all the free radicals are removed by combining two free radicals because two unpaired electrons will form a stable covalent bond. Thus, the bromination of propene is the same just like chlorination of methane. Step 1 involves bond breaking of the PR-PR bond in the presence of UV light. Step 2 involves both bond breaking and bond formation, producing free radicals that continue the chain reaction. However, in this case, we get 1 bromopropane by replacing one of the primary hydrogen and 2 bromopropane by replacing with the secondary hydrogen. The bromination reaction are favoring the secondary position due to the high stability compared with the primary position. And lastly, step 3 involves the termination reaction of the chain reaction by bond forming between any two radicals.
So let's move on to the application of free radical reactions. We have a combustion of hydrocarbons, thermal cracking in petrochemical industry, free radical polymerization, biological food and chemistry process, specialized organic synthesis reaction, and halogenation of alkenes. So for the first one, combustion of hydrocarbon. In combustion, for example in engines, power plants, and heating fuels, radicals form when heat or sparks break chemical bonds in hydrocarbons and oxygen. These radicals propagate chain reaction that ultimately oxidize the fuel to carbon dioxide and water, releasing the energy. So for the application example, efficient fuel burning in internal combustion engine and industrial burners. So for the thermal cracking in petrochemical industry, at high temperature, for example 450 to 900 degree, free radical mechanism break long hydrocarbon chains into shorter, more valuable molecule. Long chains alkane from crude oil are cracked into gasoline, Grange alkenes and alkenes. This radical initiate process helps produce raw materials for fuel and chemicals. Application example is production of lighter fuels and feedstocks for plastic manufacturing. So for the free radical polymerization, one of the important industrial use of radical chemistry is polymer synthesis. Free radical initiate the polymerization of monomers like ethene, propene, vinyl chloride, and styrene to form plastics such as polyethylene, polypropylene, PVC, and polystyrene. Initiation like peroxide generates radicals that add to the monomers double bond, and the chain grows via propagation until termination. So for the application example is plastic bag, bottles, and containers. So for the biological and food chemistries, free radicals plays a role in processes relevant to biological and food science. So for the example is like lipid peroxidation, free radical reaction with oxygen can degrade fats, especially unsaturated fatty acid, contributing to food rancidity and off flavors. In living organisms, radicals are involved in aging and oxidative stress. Antioxidants like vitamin C and E scavenges radicals to prevent damage. For the application example is understanding food spoilage mechanisms and designing antioxidant preservatives. So for the specialized organic synthesis reaction, Hans-Dicker reaction converts carboxylic acid to alkyl halides with one fewer carbon via radical intermediates. Karash addition, free radical addition to alkene used to introduce specific substituent, for example, a 3-chloromethyl group. for the application examples is used in targeted synthesis step in organic chemistry, research and specialized industry synthesis. So, for the halogenation of alkenes, is for the example used is industrial synthesis of haloalkenes.